Beams are rigid members which carry forces and moments perpendicular to their center. So here we have a rigid beam supported by a pin and a roller. This is what's commonly referred to as a simply supported beam. The pin and the roller provide a total of 3 reaction forces. If we define our coordinate system like this, x is positive to the right, y is positive up. The pin provides a reaction in the y and a reaction in the x. The roller provides just a reaction in the y. I'm going to label the left support as support A, the right support as support B, so we have reactions RAY, RAX, and RBX. Since we have 3 equations and 3 unknowns, we can use our equations of equilibrium to solve for the beam reaction force. Our 3 equations of equilibrium are some of the forces in the x direction, some of the forces in the y direction, and some of the moments around any point we choose. If we start out with the easiest one and sum the forces in the x direction, they have to equal 0. 0 is going to equal RAX. So right off the bat, we learn that RAX equal to 0. Now, if we directly went and summed forces in the y direction, we'd write an equation that would involve RAY, RBY, and P. And I'll make that a clear y. If we do this, we'll have 1 equation and 2 unknowns. So if there's 2 unknowns in our 1 equation, we can't directly solve. So the better idea is to sum the moments, and we can sum the moments at any point. So let's say we decided we wanted to sum the moments around the point load P. The point load P acts through a single point, and if we sum the moments there, there's no distance to create a moment, so P doesn't come into the equation at all. But RAY and RBY do. So if we sum the moments around P, we still have 2 unknowns in 1 equation. The best point to sum your moments around is around the point that has the most forces acting through it. That would be point A. It has RAX and RAY. We've already found RAX to be 0, but we could have just started out with this moment equation. If we sum the moments around point A, we find that 0 will be equal to P times L over 2, because it is creating a clockwise rotation, minus RBY times L, because it's creating a counterclockwise rotation. If we solve for RBY, we find that RBY is equal to positive P over 2. Now, since this came out positive, it means that we chose the correct direction for the force RBY, in that it's acting up. If this had been a negative number, we would have needed to switch the direction of our arrow around. So now we know that RBY is P over 2. We can finish off and solve for RAY by summing the moments in the y direction. The sum of the forces in the y has to equal 0. 0 is going to equal RAY minus P, because it's acting down, plus RBY. We know that RBY is P over 2. So if we solve this, we find that RAY is equal to P over 2 as well. Now, it's not a coincidence that we found that both RAY and RBY are equal to P over 2. There is a special property that a simply supported beam with a point load in the middle has, and it's called symmetry. It means that you can basically draw a line down where the point load is applied and fold the beam over on top of itself. Whenever you have a symmetric structure, you can just take the applied load and divide it by 2. And if you can recognize that a structure is symmetric early on in a problem, it can make solving for the reaction forces a whole lot simpler. As another example, here we've replaced the point load with a point moment acting in the middle of the beam. We can solve for this the exact same way we solved for the last beam. The pins, we can set up our coordinate system, x, y. The pin still gives a force in the x and y. The roller still gives a force in the y. We can still call this A. We can still call this B. We'll have RAY, RAX, and RBY. And we can go about summing our moment equations. If we sum the forces in the x again, they have to equal 0. We find that RAX equals 0. While it won't help us solve for everything directly, I'm going to sum the forces in the y first for something interesting. If we sum forces in the y, they equal 0. 0 is going to equal RAY plus RBY. Because remember, we're summing the forces. No longer do we have an applied force, we have an applied moment. So what we find out is that RAY equals minus RBY. Now, we couldn't solve this equation for any actual number, but we can still solve it for a relationship. If you're applying your equations of equilibrium correctly, it doesn't matter the order that you apply them, but if you don't do them in a logical order, you're going to end up with equations that you actually can't solve for forces right away. We could solve RAX equals 0 for forces right away. When we sum the forces in y, we find out that RAY equals negative RBY, but we can't actually calculate any final answers until we go on to the moment equation. Let's just go ahead and sum the moments around A again. And when you sum moments, if there is an applied moment on a beam anywhere, that applied moment gets tied into your moment equation. So this moment equation is going to be 0. Since we're summing it around A, RAY, RAX act through the point we're summing, so they don't come into equation. We're going to have an M going clockwise, which we say is positive, and then we're going to have RBY times L. If we solve this, we find that RBY equals M over L. Now, since this was positive, it means RBY is M over L acting up. And it's important to note that since our applied force wasn't a force, it was a moment, moment has units of force times length. RBY is a force, and that is why we have the moment divided by L as our answer. Because if you divide the moment units of force times length over length, you're left with a force. So we know that RBY equals M over L, and it acting up is correct. If we substitute that back into our sum of the forces in the y equation, we find that RAY is equal to minus M over L. The negative means that RAY is not going up, is actually in here going down. So now this beam is in equilibrium with an applied moment. Here, we've given up our pin and roller of a simply supported beam and added a fixed support on one side. When you have a fixed support on one side of a beam, we call that a cantilever beam. A cantilever beam has a fixed support, and the fixed support has a force in the y, a force in the x, and also a moment reaction. So I'm going to call this point A and say that we have RAY, RAX, and m sub a. And we just go about using our equations of equilibrium in the same way. If we sum forces in the x, they have to equal 0. 0 is going to equal RAX. If we sum the forces in the y, they have to equal 0. 0 is going to equal RAY minus P. We find out that RAY equals P. And then if we sum the moments around A, they have to equal 0. 0 is going to equal, I neglected to put a coordinate system up here, but it's the same one I've been using. MA is going counterclockwise, so it'll be minus M sub A plus P times L, and we find that MA equals PL, just using our three equations of equilibrium to solve for our beam reaction.